So we're going to talk about functions and how we can tell when they increase and decrease. So we're looking at the function f of x equals x squared. If we notice on the left side of the graph, you should notice that the graph is going down. So when x is less than 0, f of x is decreasing. When x is greater than 0, so now let's look at the right part of the graph, you notice that your graph is going up. So we would say then that f of x is increasing. So just by looking at a graph, we can see whether a function is increasing or decreasing. And when we look, by the way, we're looking starting from left going to the right, like the way that we read. Now the thing is that we are not always going to have a picture of f of x. So when that happens, what we may have is we may have a picture of the derivative, or we may actually have just an equation of the derivative. So if we take the derivative of f of x, we get 2x, right? All right, so let's kind of look at the graph of the derivative of 2x. We know that it passes through the origin, and it has a slope of 2. Okay, so it's pretty steep. But if you notice here, if we take into account, let's go back and look at f of x. When x is less than 0, the function's decreasing. Let's look at the, oops, that should say derivative. Let's look at the derivative when x is less than 0. Do you notice that the derivative when x is less than 0, the derivative is below the x-axis? Okay, and when we say, when it's below the x-axis, we say that the derivative is negative. Okay, now let's look at when x is greater than 0. Do you see that the derivative is above the x-axis? So in other words, the derivative is positive. So I want you to make this correlation here. So if we're looking at this, let's make this correlation right here, okay, between the function and the derivative. When the function is less than 0, the function is decreasing. The derivative is negative, decreasing, negative, okay? When the function is greater than 0, the function is increasing. The derivative is positive, increasing, positive. So what you want to try to do is make that connection. So if the derivative is positive, let's go backwards. If the derivative is positive, that means the function is increasing. If the derivative is negative, that means that the function is decreasing. Okay? All right, also what I want you to note is that we have what we call a horizontal tangent in the function. So in other words, a line that I can draw that will hit that curve in one spot, and it's a horizontal line. And if you look, I'm going to kind of highlight it in green here, that is a horizontal tangent. So it's hitting that parabola at 0, 0, and it's also a horizontal line. Okay? Notice what happens though. When we have a horizontal tangent in the function, look at what's happening at the derivative. So we have a horizontal tangent in the function right here at 0, 0, and look at what's happening here, the derivative. Okay? And the derivative is hitting the x-axis at that same exact x value. So a horizontal tangent, let's write this down. So a horizontal tangent, horizontal tangent in f of x, don't know why my pen's not wanting to work, that means that the derivative will equal 0 at that point. Okay? So a horizontal tangent in the function means the derivative will equal 0 at that point. So we were just talking about how a horizontal tangent at x equals 0 means that the derivative would equal 0 at that point. So what we do is then we can assume then what we call that 0, that x value, x equals 0, is what we call a critical, oh my goodness, let's maybe erase that and let's try that again. Okay, we call this a critical point. Okay, a critical point, because it's where the function is changing from decreasing to increasing. Again, it's also where the derivative is equal to 0. Now, there's going to be 3 ways to determine critical points. Right now, we're just going to be looking at where that derivative is equal to 0. So, again, let's just kind of go back and look at the original function. It was x squared. So, pretend that hits at 0, 0. There's our critical point. Now, like I said, though, we will not always have a graph of the function. So if we don't have a graph of the function, we have to go to the derivative. So if the derivative is 2x, right? And now, obviously, we know what that looks like. We're not always going to know what that looks like. So what we do is we take that derivative and we set it equal to 0, and then we just solve. And obviously, in this case, x would be equal to 0. So that would be how we would determine a critical point. Okay, so what we're going to do, basically, when we are trying to find critical points, the one way that we're going to work on for right now is to take the derivative and set it equal to 0. So when you take that derivative and set it equal to 0, you're getting a critical point. And that critical point is going to help you determine certain things about the function. So for example, here, x is equal to 0 is a critical point. Go back and look at the graph of the function, which again, we will not always have, but we just happen to have in this particular instance. So if you look at the graph of the function, notice that at x equals 0, we have what we call a critical point. In this case, that's called a minimum. Okay, a minimum because it's the lowest point on the graph. All right?